Bonjour, welcome to Wahsa Distance Education Center's radio Zoom classes. This is SVN3E, grade 11 workplace science, and I am Bronwyn Slate, the teacher. If you participate live today, you're welcome to call the Wahsa studio at 1-800-465-7144 or 737-4017. You can listen on the radio at 91.9 FM or on the television at Bell Express U channel 972. You're always welcome to join me live through the Zoom. The link is available for me, your teacher, and also your DEC. Our classes are scheduled on Monday through Thursday from 3 to 4 in the afternoon, and we are in our first week of our 9-week course. What work do you need to submit for marking once we get to that point? The key questions, the ones marked with the key icon at the end of each lesson, are the ones to submit for marking. So they're all listed at the end of each of your IL lessons. You need to do all of them. They fall into different categories. Sometimes they're called check your understanding and they're in the unit in the workbook, or their activities or review questions at the end of the workbook. So they're all listed at the end of your IL lesson. And you need to show all of your work, your steps, your thinking, all of your explanations, so that I can really understand that you understand what you're talking about. So make sure you're actually answering the question and not just writing about something on the topic. Really hone in on what the question's asking and then answer it. Also, you can do your work by hand, or you can do it electronically. So if you want to write in the workbook and send in a picture or a scan of the actual workbook pages, I'm totally fine with that. It might say in your workbook not to write in your workbook, or in your IL package to not write in your workbook, but that's fine. These are consumables, so this is yours. So you can write in it and then take a scan or a picture and send it to me. You also can, if you would prefer to type up your answers, you can do that in Word or Google Docs and then send those files to me. I don't know if you send it, if you do it in like, I can't think of what the Mac application is, Pages. If you send it in that, I'm not sure if I can access it. You can try, but it might be good if that's your method of doing electronic files. Maybe touch base with me first, just so that we can check to see make sure that I actually can access those, because I'm not on a Mac. So that'd be good to know. If you don't know how to use Google Doc, everyone has a Gmail account through NNEC. So if you'd like to use Google Docs, but you're not sure how to access them, let me know and I can hook you up with figuring that out. All right, how to submit your work for marking. So you can scan and send your work in electronically. So scan your completed work in, and if you have a smartphone, you can either use the iPhone Notes app or the Android Google Drive app. They can be a little finicky and it might take a little bit of learning to figure out how to do it and how to get it to me, but that scanning can take up less space and be easier to send than to taking a picture. If you can't scan, it's totally fine to just take a picture. That works too. Then send it to me either through email at studentwork@nnec.on.ca, and then CC it to me at bronwyn.slate@nnec.on.ca, or you can send it to me through Facebook Messenger at bslatewahsa. Either is totally fine. The second method is to drop off your work into Lookout at our location at 74 Front Street. We're the big red building next to the post office, and we have a small white mailbox next to our side entrance. So you can just stick it in there at any hours. We're currently not open to the public, so you can't come in, but you can just put it in the mailbox and then I will get it and get it back to you as soon as I can. The third method is to hand in your work to your DEC. Then your DEC can either send your work through the Express or fax it to 807-737-1732 or toll-free fax to 1-800-463-7852. If you'd like to connect with me through social media, my Facebook, and then I also have a YouTube channel called both under the name Slate Wahsa. You can friend me on Facebook or subscribe to my YouTube channel, and then you'll get notifications whenever I upload one of our radio Zoom classes. So our radio Zoom classes are recorded, and then I upload them to YouTube to a playlist called SVN3E. So all of our classes are in the same place, and I share that on Facebook. our class at the end of my workday, so most likely I will upload it the day after in the morning. So it won't be up immediately after airing, but it'll be up then within the next day, within 24 hours. Science, like most learning, is incredibly visual. So accessing the replays or the Zoom is going to set you up for the most success. So I really encourage you to join me live or to check out the YouTube videos afterwards, after airing, so that you can really get the full experience of the learning. I have lots of images and some videos that I'm linking to in terms of other YouTube videos, that being able to see what's going on is really going to set you up for the most success for understanding what it is that we're talking about. If you don't have reliable internet, feel free to let me know, and then I can send you the recording of the like video files on a USB key or something so that you can access them even though you don't have reliable internet. If you have any questions or concerns, please contact me. My email is bronwyn.slate@nnec.on.ca. And that's spelled BRONWYN.SLATE. My Facebook is Slate Wahsa. You can call me at the office and leave a message for me. I'm still working remotely this week, but I'll be back in the office next week. It's 807-737-1488, or you can call me toll free at 1-800-667-3703. And my office hours are Monday through Friday, 9 a.m. to 4 p.m. And I'll get back to you as soon as I can within those hours. Before we dive in too much, I just want a reminder of my positionality. So I, as a teacher, have white Southern ancestry, and that means that I come to science and to all education with a certain bias because I have grown up with a lot of privilege, with white supremacist privilege, and therefore the way that I walk in the world is slightly different than others. I do live in Northwestern Ontario on the traditional territories of the Anishinaabe people, and so I honor them and recognize the wealth of knowledge around me. But this is also my first time teaching this course, so I have lots to learn about this subject, and also have lots to unlearn because of the ways that I have been taught in our white supremacist education system, and that just sort of alters my lens. And I'm trying hard to acknowledge that and to change that, but it is a reality. Also, our textbook is very Eurocentric, so it really focuses on the idea that Europeans discovered lots of things or established in science lots of things, and this, though they are part of the story, they're not all the story. In many places in the world, many folks have discovered really useful, really fascinating scientific facts and knowledges, including Indigenous peoples. And so it's really important to honor those and to recognize those knowledges and experiences. Our textbook generally ignores Indigenous, Inuit, and Métis knowledges and experiences, and so I will try to pull those in as much as I can. It also may use some problematic language, which I will try to correct and be aware of. If there's anything that I am doing that is problematic, I encourage folks to let me know so that I can learn and improve. All right, so diving into our unit. So we are starting unit 1 today, and this is called We Are the Guardians of Earth's Spheres. So this is on the idea that Earth is a superorganism, so meaning that all living and non-living parts keep the Earth healthy. That all of Earth's spheres, so the land, soil, the air, and the water, are connected to one another, to us, and to other life forms. So it's all interconnected, having impacts on each other. So in this unit, we are learning about these spheres and how people specifically affect them, and overall how that affects us, and how we figure that out and what the overall impacts are. So today's lesson, we're starting lesson number 1 in our workbook, and is just learning about the components of soil, water, and air. So sort of scientifically looking at those 3 spheres of the Earth. And then in future days, we will dive in further in terms of impact upon them and how we analyze that and how we learn from that. So our learning goals for this lesson are that at the end of this lesson, you can say, I will be able to identify and describe components of soil, water, and air. So hopefully you'll have a good understanding of those three components that make up our Earth. Success criteria, so how you know that you've met your learning goals. You can say, 1, I can explain the components of soil and the impacts of porosity. 2, I can describe the water cycle as well as how acidic and basic solutions work. And 3, I can explain what gases make up the air and their importance to living things. At this point, if none of that makes any sense, that is completely fine. It's just giving you an idea that at the end, hopefully you can understand these things. And then you know that, yes, you've covered this lesson and you're feeling confident with this material. All right, so we're going to start with soil. So first off, what is soil? So soils are complex mixtures, lots of things, of minerals, of water, of air, of organic material, and of various decaying organisms. So here is a pie graph that shows us the ideal components of soil. So this would be the ideal ratios. 45% of a sample of that soil would be mineral content. So rocks and minerals are that matter. Then 25% is air and 25% is water. And then 5% is organic material, which includes various decaying organisms. That would be organic material. So both plants and animals, decaying animals. So that is the ideal soil. Lots of soil is not ideal, but that is sort of what is the healthiest kind of soil. Soil forms the surface of the land. It is the skin of the earth. And it's capable of supporting plant life and is vital to life on Earth. So soil is one of the foundations of what means that we can survive as well as everything around us. All right, so let's dive into organic matter a little bit more. So organic matter contains plant, animal tissue, bacteria, fungi. So it can be things that are really, really small, microscopic things that we can't see with the naked human eye, but all contribute to organic material. This all falls generally in the humus, sorry, I say it wrong. When the organic matter is very well rotted and decayed, the result is a crumbly dark dirt. So this is found at the top layer of our soil, and we'll look into more of this in a couple of days. But this is the rich soil that is really good for plant growth because of all that nutrients that comes from the organic matter. Humus helps soil to hold water, which gives plants nitrogen, phosphorus, and potassium. These would be different minerals, different elements that are vital for plant growth. All right, so we're going to watch a little bit of video about air being present in water, and we're hoping it's going to all work smoothly for us.
Air is present in the soil, just as there are animals that live in water. There are also animals that live under the surface of the soil. These animals also require air to live. The following activity demonstrates the presence of air in the soil. Dig out a small lump of soil from your garden. Place this lump of soil in a small vessel. Pour a small amount of water on it. Bubbles are observed coming out of the soil. This is because the water molecules displace the air present between the soil particles, and the air rises and escapes from the surface as bubbles. This air is utilized by the organisms living in the soil, such as ants, beetles, and earthworms to respire. The animals that live under the soil make deep holes and burrows in order to facilitate the free flow of air within the soil. Earthworms are especially popular in this aspect and are known as farmers' friends, since they keep the different layers of soil under continuous rotation, thereby keeping the soil fertile. It has been observed that a lot of worms and animals that live inside the soil come out during the rainy season. This is because the water from the rain displaces the animals in the soil, making it hard for the animals to respire. Soil is thoroughly ploughed before the cultivation of crops, so that there is always a steady flow of nutrients, water, and air.
All right, so that just gives us an idea that reminds us that though we think of these Earth spheres of earth, air, and water, or soil, air, and water as three separate entities, they actually are interconnected, and there is air and water within soil, and then even within water, there is air and soil, and within air, there is actually water particles and soil particles as well. So they're all interconnected in different ways, and that's really important to remember. All right, so then also looking at minerals. So minerals are small rock pieces. They're particles that have been broken up over thousands of years. And they get broken up through ice, rain, wind, and other natural forces that we call this weathering, that beat on them, that they break them up into smaller and smaller pieces. Minerals are contained by rocks by different sizes. So it's defined by their size, their diameter. So we have sand, which is 2.0 to 0.05 millimeters, which here is a visual that shows you what sand looks like. Then we have silt, which is from 0.05 to 0.002 millimeters. So this is getting very small. And that's this silt is here, it's crumbling. And then we have clay, which is less than 0.002 millimeters. So this is very, very small particles. And the clay is usually really, really dense and hard to see the individual particles at all because they're so fine. Whereas sand, generally you can see those, the different grains of sand. So sand creates pore spaces, and the silt and clay provides nutrients. So it provides phosphorus, potassium, sulfur, magnesium, boron, and zinc are some of the examples of the nutrients that they provide, which helps for plant growth. And then the sand helps create those spaces where water and air can be in, so that helps keep the soil fertile as well. Here is a graphic of porosity. So porosity is talking about those pores. So porosity is the pore space in the soil. So this contains air and water, which contain gases like oxygen, which continue to or add to the health of the soil. So if there's no oxygen in the soil, plants die. They need the oxygen. If there's no water, then the plants die. If there's no nutrients, then plants die. So the porosity really affects the chances of plants being able to grow in that soil. So they need a certain amount of porosity in order to thrive. However, having too high of a porosity is not good, and having too low is not good. So looking at this graphic, we can see that if there's no pore spaces, so it's non-porous, it's non-permeable, means that all of the mineral matter, all of the grains of soil are really compact, are really close together. There's no space between them. So there's no chance for there to be air or water, or even the chance for roots to get down in there. There's no opportunity for growth. It's just really, really hard packed particles, and therefore there's no space for plants. Whereas if we have unconnected pore space or connected pore spaces, so there's lots of room around our grains of soil. So this is very porous or permeable, then your water is just going to run straight through these grands. There's nothing, it doesn't get caught. And therefore that's really hard for plants to grow as well, and to thrive. The majority of plants, some do well, because the water is just running deeper and deeper, and then they're harder to reach. So having some unconnected pore spaces, and so this is porous but non-permeable, this is a good for many, many plants having this amount of porosity, because it's sort of a balance between having things too tight and not being able to have any space for water or oxygen, or having too loose and everything just running away. Sorry. Okay, so we're going to watch another video this one compares shows water running through sandy soil, clay, and loam soil. Loam soil is sort of a combination of all three, including silt. So I couldn't find one that had just silt in it, but this is a pretty good approximation of what those three things, what would happen if we were to pour water in them, and see how the effects of it. Hopefully it's going to load.
Soil is formed from the breakdown of rocks and minerals on the Earth's surface through weathering and erosion. Soil is important for growth and life of plants. It helps hold the plants straight up and a source of nutrients and water which the plant uses for growth and living. Let us learn more about the three types of soil. Sandy soil consists of small particles of weathered rocks. It has the largest particles among the three types of soil. Its texture is rough. Drainage system and aeration are good. However, it has low nutrients and poor water holding capacity. Clay soil. It has the smallest particles among the three types of soil. Its texture is fine and rich in nutrients which plants need. The soil particles are tightly packed with very little or no air space. The soil has very good water holding capacity. Clay is the densest and heaviest type of soil which does not drain well. Loam soil. It is a combination of sand, silt, and clay. Its texture is rather fine. It's black or brown because of a high amount of humus. It has the ability to retain moisture and nutrients. In this experiment, we will test the water flow and absorption in each type of soil. I prepared 3 cups with holes at the bottom.
She's just filling the cups with, first she did loam, now she's doing sand, and now she is pushing clay in. The clay is really, really firm, so she's trying to get it all really solidified and to the edges of the cup so you can really see the seal. Now she's balancing the cups with the soil in it with little cardboard holders.
The water is measured and the timer is set.
So now the water is poured into the cup and draining into a cup below. The sandy soil took 1 minute and 11 seconds to drain through. Clay soil took 1 minute and 15 seconds to drain all the water through. And the loam soil took 1 minute and 17 seconds for the water to drain through.
I am expecting little amount of water for the clay soil, but it turns out to be the opposite. Why? Based on my observation, the clay soil is already wet. Therefore, it will not absorb much water. Also, the water made its way on the sides of the plastic cup, not through the soil. On the other hand, sandy soil is dry, so it absorbs some water. Also, as expected, the water passed through the sand real fast. Loam soil is also dry. It absorbs more water than sandy soil. Some water passed through the soil, and was captured by the cup at the bottom. Let us do part 2. This time, all the 3 types of soil are wet.
So she's repeating. This time she has dampened the sand and the loam, and repeating, pouring the water through to see what happens, capturing it to see how much has come through. She's now measuring to see how much, and each of the water cups were given 1 minute and 30 seconds to drain completely to see how much drained through.
For the results, sandy soil and clay soil did not absorb water anymore, while loam soil absorbs 5 ml of water.
That just gives you a little bit of a visual to see, hope if you're watching the video, of what we're talking about when how the sand, silt, and clay are different and how that affects plants' growth. All right, so now that we've talked about soil, we're going to talk about water, the water sphere. So, sorry, for some reason, my thing has gone to the wrong slide. Anyway, okay, so first vocabulary for water. We need to know, this is actually true for all elements, but it comes in more into play with when we're looking at water specifically. So this is just general science vocabulary that is good to know because it's going to keep coming up over time. So first, atoms are the smallest part of matter. All matter are made up of atoms. Elements are matter that is made up of only one type of atom. So there are, I don't know how many types of atoms, probably a lot of different types of atoms, and elements are when you only have one type together. So here on my visual, I have Na, which is sodium, S, which is sulfur, P, which is potassium, I can't remember, C, which is carbon, N, which is neon. I see if this is bad. Anyway, blanking, oxygen, hydrogen, chlorine. So these are different elements and they only have, like, an oxygen element only has oxygen atoms in it. A compound has 2 or more different elements combined or bound together. So here we have an oxygen bound with 2 hydrogens, and so that's H2O, which is the chemical makeup of water. Here we have a carbon bound to 2 oxygen, so this would be CO2, so carbon dioxide, and this would be what the molecular makeup of that. That's the compound that makes up carbon dioxide. So then, knowing the structure of an atom, so an element in our compound are made up of atoms. Then there's little parts that make up, that are a part of atoms. So the nucleus is the group of neutrons and protons at the center of an atom. Neutron is an uncharged part of an atom and it's found in the nucleus, so in the center of the atom. An electron is the part of the atom that is negatively charged and orbits the nucleus, so it is a negative particle that flies around the atom. And a proton is the positively charged particle of the atom and it's found in the nucleus with the neutron. So here's a blown up version of an atom. So here you can see the nucleus is this blob in the middle, and it has neutrons, which don't have a charge, and protons, which are positive, and then the electrons are moving around outside the atom. The number of neutrons and electrons protons define what the atom is, and the electrons define the charge of the atom and how that is going to act. So that is just all important as we move forward to remember those terms. So I'll be using them and understanding what's going on. So solvent is a substance that can dissolve another substance. And an ion is an electrically charged particle. So you either have positive ions or negative ions. And ionization is when an atom gains or loses an electron. So it can pull electrons from other atoms or it can give its electrons away. So here we have, we're looking at a jar of water and it has salt in it. And we're seeing that the compounds of water are pulling away from the salt because of their charge. So we're going to look at that a little bit more. Water is called the universal solvent. Wait a second, what is this? Okay, sorry, my bad. Okay, water is a universal solvent. So this is because it dissolves so many substances. It does not dissolve all substances, so it really shouldn't be called universal, but it dissolves a lot of different things. Not letting me, sorry, I want it to have video attached and it's not letting me select my video. So I'm just trying to figure out. I don't know if it's because I'm on the laser. It's just not liking me. Just 1 second. Come back through. There we go. Of course, it wants me to update. Things are just not working for me. Okay.
Video, I'm going to teach you about water and its role as the universal solvent. In the process, I'm also going to show you how polar solvents rip apart polar solutes when they dissolve. First, let's remember a few things. 4 things specifically. First, water is polar, and that means that its molecules act like little magnets with positive and negative ends. Second, a solute is dissolved into a solvent to form a solution. These are the vocabulary words we use to describe the dissolution process. Third, solubility is a measurement of how well one thing dissolves inside another thing. Finally, solubility is high when the solute and solvent have the same polarity, so they're both polar or they're both nonpolar. Now that we have that review, let's get started. Water is called the universal solvent because it can dissolve an extremely high number of chemicals. Water's polar nature allows it to dissolve almost any other polar molecule inside itself. So water is H2O, oxygen is partially negative, and the hydrogens are partially positive. So it acts like a little magnet. So we're going to be looking at this process where salt crystals get dissolved into water. We're going to see what happens as the crystals seem to disappear. Our salt crystal on the left, and water on the right. Salt is not an equal one. Salt crystal is this part of the salt crystal. That's so
Great. So that gets us a little bit more understanding of water as a universal solvent and also how things dissolve. All right, so we also need to understand the water cycle when we're thinking about water spheres, or the sphere that's water. So we have our surface water, so water on land, ponds, lakes, rivers. We have groundwater, so water that's in the soil or on the rock below the Earth's surface. We have evaporation, when water is heated and it moves from land and the surface water to the air and becomes water vapor. We have precipitation, when water vapor cools and creates clouds, then falls as rain, sleet, and snow. And we have runoff, when precipitation falls on the land and then flows onto the surface to lakes, rivers, and oceans. And then we also have percolation, which is when surface water moves into the ground. So here is a visual with the water cycle. You may have seen something similar that doesn't have quite as much language on it. And you don't need to know all of this, but this just sort of gives you the information of that water comes down as precipitation out of the sky and runs off and collected into the surface water, or it's infiltrated into the ground through the ground, or it's percolated between the surface water and the groundwater. And then it all flows into the ocean, and then it evaporates either from water or land. It can evaporate from the land as well. And then condenses into clouds and precipitates again and goes around and around. So that is a water cycle and how our water rotates through our Earth. Then we also need to understand acidic and basic solutions when we're talking about water and the Earth. So first, acids are substances that produce hydrogen ions when dissolved in water. So we have our water molecule here, H2O, and our hydrogen is one of our H's, and they're positive charged because they're negative. The one electron is stuck with the oxygen. So this is when you have more hydrogen ions. So the more hydrogen ions you have, so the little hydrogens floating around by themselves, the more acidic your solution is. It tastes sour, though I'm not suggesting that you taste all acids. That's not safe. And really strong acids corrode, so they damage or eat away metal and other substances. They can cause severe skin damage that feels like a burn, and they are poisonous. But also vinegar is a common acid, or lemon juice, things like that. So not all acids are poisonous or going to harm you. We consume some acids. It's just a spectrum of what is safe and what is not. So then a base is a substance that produces hydroxide ions, so OH negative ions when dissolved in water. So here's the opposite. When you have your water, you lose a hydrogen, so then you have a positive hydrogen floating around, and then you have also your hydroxide ions, which is an OH negative ion floating around. So the more hydroxide ions, the more basic or alkaline the solution is. It tastes soapy or bitter. Strong bases are caustic, so they also damage and eat away, but they do this to organic substances. So it still can cause severe skin damage that feels like a burn. So it's not like one is really safe and one is dangerous. They're both dangerous as the higher their levels are. And baking soda is a common base. So they're also safe bases that we use frequently. So we measure acids and bases on the pH scale, and pH stands for the power of hydrogen. So here's a visual that shows you the pH scale and some examples. So we measure, the pH scale is from 0 to 14, and 0 is the most acidic. So batteries, stomach acid, lemons are all very acidic. And then you can see other examples. Coffee and milk are not as acidic, but still are on the acidic side of the neutral. Water is neutral. It doesn't have, generally has, it's a neutral pH scale. And then as the numbers get higher, we're getting more alkaline or basic is, we use both those terms. So blood is more basic or alkaline, baking soda, stomach tablets, so like Tums, soap, drain cleaner, bleach, those are all more, they have a higher pH scale and have are bases. So now if you'd like to pause the video and do some of your key questions. So on page 6, there's our 3 check your understanding questions that you should be able to answer now. And then finally, we have a few more minutes to talk about air. So air is a mixture of gases, and it's always going to be slightly different, but generally air is made up of mostly nitrogen, so N2, and most often it is around 78.1% of our air is made up of nitrogen. And then oxygen, O2, which is 20.9%, which in my child brain, I would always, you think that air is oxygen, but a very small portion of the air actually is oxygen. Well, it's a large chunk in comparison to other things, but it's not as much as nitrogen. Then there's water vapor, which is 0 to 4% water of the total air volume. And then carbon dioxide is 0.036%. And then it continues. So methane, nitrous oxides, carbon monoxide, ozone, sulfur dioxide. So these are all small amounts, and there's even more things that can be smaller and less of them. But these are the things that have effect on our environment. These are the chemicals that do. So carbon dioxide and oxygen. So plants and animals need oxygen and carbon dioxide to live. The carbon cycle explains how the gases move within the Earth spheres. So we are going to watch a short video about carbon cycle. Oh. All right, so that gives you a little bit of an understanding of carbon in the air. And then also we want to look a little bit at nitrogen, as these carbon and oxygen and nitrogen are the largest amounts of our air. So nitrogen are needed for all living things, but few organisms can get it directly from the air. So even though most of our air is made up of nitrogen, most living things can't actually use it when it's in the air. So the nitrogen cycle explains how the large amount of nitrogen that's in the air becomes usable by living things. So we are going to watch another quick video for our last few minutes about the nitrogen cycle. Returns to the atmosphere. So must be now. All right, so that gives us an overview of the nitrogen cycle as well. So now you can answer the key questions on page 7 of your workbook, which you check understanding questions 1 and 2. So let's do a quick highlight reveal of what we've done for this lesson as we wrap up. So we looked at the components of soil, water, and air. So soil is made up of air, water, minerals, and organic materials. The mineral composition of sand, silt, and clay affects the porosity. Water is a universal solvent. The water cycle shows us how water moves throughout the sphere, and acids and bases are important to understand, and the pH scale is that all impacts water as well as other solutions. And then air is made up of various gases, specifically carbon and oxygen and nitrogen are the largest components of air, and that has an impact on the growth and healthiness of all living things. So our success criteria are that 1, you can explain the components of soil and the impacts of porosity. 2, you can describe the water cycle as well as how acidic and basic solutions work. And 3, you can explain what gases make up the air and their importance to all living things. So hopefully at this point you can do all those things. If need be, to go back and reuse the and slow things down, check to try some of those questions, but hopefully this all makes sense. And now you can do the key questions that are on page 9, the review questions, 1 through 12. Again, remember, you are welcome to write in your workbook if you'd like. They don't give you a lot of space. So if it makes more sense to write on different paper or to type it up on a device, that is totally fine as well. If you have any questions, please contact me. This is what I am here for. I'm your teacher. I am here to help, though it is really hard for me to do it from afar if you don't reach out. So if you have any questions or anything you're struggling with, let me know. My number of the office is 807-737-1488 or toll free 1-800-667-3703. My email address is bronwyn.slate, which is spelled BRONWYN.SLATE@nnec.on.ca. You can connect with me through Facebook at Slate Wahsa, and you can subscribe to my YouTube channel at Slate Wahsa, where I will upload this video as well as our other lessons as we go through them. My office hours are Monday through Friday, 9 to 4. So I'll get back to you within that time frame if you reach out to me. Thanks so much for joining me today. And next lesson, we will dive into the human impacts on soil, water, and air. Miigwech!